concentration of A, B inlet. Let's draw the picture. V in and CA in. CA and V out, CA out. And the assumption of the CSTR is that CA is equal to CA out. This is the main CSTR syntax. I don't remind me again. So I'll start writing big ones, sometimes I regress. If we divide both sides by the volume, so we divide the equation by the volume, then since the volume of the reactor is fixed, it doesn't change, I can bring the volume into the derivative, and I have dCA dt. Because I bring the volume inside the derivative because the volume is constant of the reactor, unlike a batch reactor where the volume may change. And then here I have V in over V. So I have CA in over, and what we're going to do is look at a special case of constant density. And if it's constant density, that means V in equals V out. That's constant density. So I can drop the in and the out, and I can just call them V. And then I can define tau, the space-time, as the volume over little v. And we said the space-time was the amount of time it characterizes a flow. It's the amount of time it takes to flow one volume's worth of reactor, one volume's worth of fluid into the reactor. So in that case, little v over big V is the inverse of tau. So I have 1 over tau here. And then here I have a CA out, which we said is just CA. CA out equals CA. And then I have plus RA, where RA is the rate of production due to reaction of A in moles per unit volume time. And I have to, and actually I would have had the V here, so then the V's cancel. So this is the special case of constant density CSTR. And let's look at this for a second. Let's rearrange that equation. So notice I have dCA dt, and I have a CA on the right. So I can bring that to the other side of the equation. CA over tau is equal to CA in over tau plus R. So this is a typical CSTR equation, and of course the R rate depends on the reactions that are going on in the reactor. Now I want you to notice that on the left-hand side I have a derivative, and then I have something linear in CA. And then I have something that has nothing to do with CA on the right. It only has to do with CA in plus RA. And RA depends on the particular problem. But immediately you can see that I have terms that look like a derivative of CA and then something times CA on the right. So let's look at a particular problem, the problem we started looking at last time. The problem we started looking at last time is we have a CSTR, and for t less than 0, it's at steady state. And if t equals to 0, it's steady state, and I have a CA in for t less than 2. And at steady state, I have a step change. CA in changes to CA in for t greater than 0. So if I plot CA in versus t, it goes like this, where this is t is equal to 0. It goes from one value to another. So before t is equal to 0, the reactor was at steady state. Nothing was changing. Now I change CA in, and all of a sudden, things are no longer steady, and CA out is going to change with time. So before this, I had CA out, CA versus D, was at some steady value, and now this changed all of a sudden, and there's going to be something going on here until eventually it reaches steady state. And we want to find out what this is. how does CA change with time? Now, you can notice, CA in, if I change CA in, it gets instantly mixed with everything else. But most of what was in here is still the old CA in, not the new CA in. So I get some sort of mixture. And eventually, if there's no reaction, eventually what will come out will be the new CA in. Here we have no reaction already. So this is all given. So what we want to find out is how CA changes with time. And if we look at the equation, that's the equation with RA is equal to 0. If RA is equal to 0, this is my equation. And that equation is of a general form that we're going to be seeing a lot of. So we want to solve it once and for all instead of having to do it a million times. So let's write out that equation. Let's say it's dy dt, where I'm going to make it look general, but instead of calling it CA, calling it y. Because sometimes we'll have equations where y is the temperature instead of CA. Plus A of t y. Here, what's multiplying CA is a constant, but sometimes it might depend on time. And that's equal to B of t. Well, here, B of t is also independent of time. It's a constant, but in more general cases, it might depend on time. And let's see how to solve this equation. Does anyone remember from ordinary differential equations, which I asked you to review, how you solve an equation that looks like this? You were going to review your ordinary differential equations, right? Good. Use an integrating factor. And the integrating factor is e to the integral of a ds, a of s ds, where I integrate to t, but the lower limit is when the change happened. Now, in this particular problem, the change happened at 0. But the change doesn't have to happen at 0, it can happen at some time t1. So let's keep it general from t1 to t. Now why do we do that? Because when I multiply this times the left side, I get something that's d dt of e to the integral t1 to t, a of s dx, times y. That is, it turns the left-hand side of the equation into a total derivative. And the right-hand side is whatever it is. It's b of t, e to the integral t1 to t, a of s dx. Now, notice, how do I know this is this times integrating factor is a total derivative? Well, I can use the product rule. The derivative of the product is the derivative of y times the exponential, dy dt times the exponential, plus y times the derivative of the exponential. Y, the derivative of an exponential is the exponential back, times the derivative of the thing in the exponent. The only place I have t is up here. And the derivative of the integral is the integrand evaluated at the upper limit times the derivative of the upper limit. The upper limit is t, so t is 1. So I just get a. And now I can solve this because this is a total derivative. So if I solve this, I multiply by dt. And I integrate both sides. And I integrate from t1 to some, and I'm going to call this a t prime, because I can't have the same limit of integration as the variable of integration. So I call this a dummy variable t prime, and I integrate up to t. And here I integrate from the lower limit at t, at t1. From e to the integral t1 to t1, a of s ds, times y of t1, to the upper limit is e to the integral t1 to t, a of s ds, y of t. That's a little messy, so why don't I write the upper limit here? The upper limit is the integrand evaluated at this is the integral of the total derivative of d something. So just, so what do I get? I just get e to the integral t1 to t, a of s dx, y of t, minus the integral from t1 to t1. What is the integral from t1 to t1 of anything? What's the area under the curve if I only have 1 point? 0. So this is just e to the 0 is 1. So I have minus y of t1 is equal to the integral from t1 to t, e of t times e to the integral t1 to t prime, a of s ds dt prime. And that, depending on what this is, I have to do for any given problem, I have to do the integral that way. But let's just solve for the answer. So I want to isolate y of t. So it tells me y of t is equal to y of t1 times e to the minus integral t1 to t, a of s ds, plus the integral plus e to the minus integral t1 to t, a of s ds, times the integral t1 to t, b of t prime, e to the integral t1 to t, a of s ds dt prime. And this is the t. So this is the general solution. And that way we've done it once and we don't have to do it again. We'll refer to it. And let's just look at the special case where a is a constant and b is a constant. Special case, a and b are constants. So then it gets simpler when a and b are constants. When a is a constant, a comes out of the integral, and this is just e, this just becomes y of t is equal to y of t1 times e to the, well, if a is a constant, it comes out, and I just get a minus a t1 minus t. Actually, I should make it plus, let's do it the other way. Here we go. I'm integrating from here. E to the minus a t minus t1. Because a comes out, and I just get t1 minus t minus t1. And on the bottom, I have plus e to the minus the same integral, a t minus t1, times the integral. Well, actually, b comes out. B comes out of the integral. So I get b is constant. And now I integrate times the integral. E comes out, and I have the integral of e to the a t prime minus t1. Well, let's write that out. So I have to do that. I don't want to muck this up. I'll just put the answer here. So I'm taking the integral of e to the a t prime minus t1 dt prime. I want to do that integral because that's what's going to go in here. That's this thing. And this goes from t1 to t. All right, well, I can integrate this, and this is dt prime. Well, notice t1 is a constant, so I can notice that I can change variables to t prime minus t1, and just change the limit of integration. If t prime is t1, t prime minus t1 is 0. And if and then all I have to do is take t minus t1. So I change variables from t prime to t prime minus t1. And this is e to the a t prime minus t1. So now I have the same variable here as I have here. So this is like e to the ax dx. So the integral of that is just e to the ax divided by a. So this is just 1 over a, e to the ax, e to the a this. At the top, it's e to the a t minus t1 minus e to the 0, which is 1. Is that clear? It's a little bit of calculus. So I get a 1 over a here. And notice here I have e to the a t minus t1. And here I have e to the minus a t minus t1. When I take this and I multiply it by this, I get 1. And when I take it and I multiply by minus 1, I get it back. So what I get here is b over a times 1 minus e to the minus a t minus t1. So this is a special case, and this is a general case. Are there any questions on that? So it's a little, remember I told you there's a lot of math in this class. This is not difficult, this is algebra, but it's easy to get lost. So if you get lost in a step, ask me. But these are the general, these are the equations. So what I'm going to do is, we're going to be using these solutions for the next week or two. And I'm not going to rederive this every time. So I'm going to write this out on a piece of paper and print it up and give it out to you. So whenever we need it, you have it. All right, so let's get back to the problem we were working on. The problem we're working on is what happens over here. Well, if RA is 0, here is my equation. And in this case, what is A? If I compare this to the general form here. So if Y is CA, what is multiplying Y here? What is A? A is 1 over tau. And what is B? What is B? B is what's on the right side of the equation. So what's B? Volunteer? No, this is B. Somebody else? Somebody back there? Remember, your job in class is to pay attention. Otherwise, there's no point in being here. What is B? Yeah, just read it to me. CA in over tau. And RA is 0 in this problem. RA is 0. RA might have a CA in it. So that's why I'm not doing this in general, I'm doing it for this. If it has a CA in it, I might have to move it to the other side. But for this particular problem, this is what I have, and I have the solution here. So the solution is, immediately, y of t, and both of them are constants, a and b are constants in this problem. So I have CA of t is equal to, it's equal to, now in this case, let's actually identify this. Y, let's identify here. Y is equal to CA. T is T. We already said what A and B are. And T1 is 0 here. Because the step change, I said, happened at 0. It didn't have to happen at 0, but it happened at 0. So now let's plug in. So I have CA of T is equal to CA at T1. CA 0 times e to the minus A is 1 over tau, times t minus t1, t1 is 0, so it's t. And then I have plus b over a. B over a is CAN over tau over 1 over tau, it's just CAN. And this is CAN for t greater than 0. Because I'm looking for the solution at t greater than 0. Times 1 minus e to the minus t over tau. And if I want to rearrange this, let me subtract CA of 0. So CA of t minus CA of 0 is equal to CA of 0 e to the minus t over tau minus 1, because I subtracted the CA of 0, plus CA in t greater than 0, 1 minus e to the minus t over tau. So I just copied this term. I copied this term, I subtracted the CA of 0. And I want you to notice that here I have the negative of this quantity. So I can rewrite it as CA of t minus CA of 0 is equal to CA in at t greater than 0 minus CA of 0 times 1 minus e to the minus CA. And now I can look to see what the solution is here. If I look at the solution, well, first let's figure out what the initial condition was. We said the initial condition was, what was this value here? CA of 0. Well, CA of 0 is what would happen if I, at steady state, when t goes to infinity. When t goes to infinity, this is 0. And I have CA of t minus CA of 0 is CA in minus CA of 0. So, yeah, let's see exact CA out. Actually, well, let's see if there's a nice way to do it. Yeah, let's just look directly at this. What was CA of 0? CA of 0 was this equation when t was less than 0. Because the system was at steady state before I introduced this step change. It was at steady state at a value of CA in for t less than 0. So steady state means I let t go to infinity. So this term drops out, and this drops out. And that says that CA at infinity, that is the steady state value, which I had before I started, was just CA in at t less than 0. So for this problem, I know that CA for t less than 0, which was at steady state, was equal to CA in for t less than 0. And that actually makes sense, because what was happening? I had CA in coming in, and nothing else coming in and no reaction. So in steady state, I would also have CA in coming out. So I know that CA in at t less than 0, CA at t less than 0 this is CA equals 0. This thing and this thing is nothing more than CA in at t less than 0. Actually, let me not write it there. Let's notice, so this is CA at t equals 0 is equal to this. So if I want to plug in here, this would be equal to CA in at t less than 0, and this would be CA in at t less than 0. So let's notice what the solution looks like. The solution says CA minus CA 0. The value minus this value is equal to a constant, which is the difference in CA in. CA in t greater than 0 minus CA in t less than 0. This distance. This is CA in t greater than 0. And this is CA in t less than 0. So it's this difference is exactly this times 1 minus an exponential. 1 minus an exponential looks like this. So that tells me I know exactly what this looks like. It looks like this. Because this is the 1 minus an exponential. And the final value, the value at infinite time, new steady state. So this initially was equal to CA in at t less than 0. The same thing happens here. Eventually, as t goes to infinity, this drops out, and I have CA of t at infinity goes to CA in at t. So this value is CA in at t greater than 0. And that's because there's no reaction. So let's notice that this value is the same as this value, and this value is the same as this value. But what happens in a CSTR? When the input is a step change, the output, so here I have a discontinuity in the function itself. Notice here, it's continuous, I have a discontinuity in the derivative. So in a CSTR, when I have a discontinuity in the input, the output only has a discontinuity one derivative higher, first derivative. And you can imagine if I had, and we'll get to it later in the hour, two CSVRs in series. If I have a discontinuity in the inlet to the first CSVR, then the outlet has a discontinuity in the derivative, not in the inlet, in the derivative. And the outlet of the second CSVR will have a discontinuity in the second derivative. So it will have a smooth derivative, but a discontinuous second derivative. So that's what you can anticipate, and we will show that in great detail. Are there any questions on that? Okay, so why don't we see, yeah, okay. Yeah. T prime, it doesn't make sense to have the same variable in the limit as in the integral. Because when you integrate the variable in the integral, it disappears. So that's called a dummy variable. So I needed to change t to something else to make it a dummy variable because I want t in the solution, not coffee. Is that good? All right, so now I might ask, let's look at a couple of things. We can define something called the steady state gain, KT. And KT is defined as, a definition is a colon time with an equal sign. KT is the change in the output divided by the change in the input at infinity, at steady state. So let's see what that means. That means CA at t goes to infinity minus CA to 0 divided by CA in at t greater than 0 minus CA in at t less than 0. So let's see what that is. CA at t goes to infinity, well, we said that was equal to CA in at t greater than 0. And CA initial, that was steady state before the jump. Steady state before the jump was CA in at t less than 0. Divided by CA in at t greater than 0 minus CA in at t less than 0. So in this problem, the steady state gain is 1. Now, this is an unusual problem and it's kind of a dumb problem because there's no reaction. So the steady state gain is 1. Once we introduce a chemical reaction, there'll be other things. Now, I can ask the question, how long does it take? So if this is t is equal to 0, what is the amount of time it takes to reach 90% of the gain? If the total gain is this, how long does it take? So if this is delta CA in, I might ask at what time do I reach 90% of this, 0.9 delta CA. So at what t star do I reach 0.9 delta CA? So, question. At what t star do I reach 0.9 times, well, do I reach CA minus CA in at t greater than 0 is equal to 0.9 CA at t goes to infinity minus CA in at t greater than 0. That was CA minus t less than 0. So I know when t goes to infinity, I'm going to make this jump. How long does it take me to make 90% of that jump? So that's the question. How long does it take me to make 90% of that jump? Well, notice here I have CA of t minus CA in, because CA of 0 is CA in for t less than 0. And here I have this CA in at t greater than 0 minus CA in at t less than 0. That's the final. This is CA at t goes to infinity. So the question we're asking is, when is this 90% of this? In other words, when this is 90% of this, that says this is 0.9. So the answer is 0.9 is equal to 1 minus e to the minus t star over that. Is that clear? Remember, this is we have to identify what's what. CA of 0 was the steady state at the beginning of the problem. That is, it was a steady state for CA in for t less than 0, t less than 0. CA at infinity is CA in at t greater than 0. So this we can just rearrange. E to the minus t star over tau is equal to 1 minus 0.9 is 0.1, or 1/10. So if I take log of both sides, I have minus t star over tau is equal to minus log of 10. I add that t star is equal to tau log 10. And they give you numbers in the textbook. So the log of 10 is 2.303. And whatever tau was, you get t star. So is that clear what we're doing here? You get t star. Again, if you don't understand something, stop me and ask. The whole goal of you being in class is for you to understand what's going on in class, so that when you look at the book, there are no surprises. So don't be shy. If there's anything you don't understand, just ask. I don't mind being interrupted. Well, okay, so let's even come up with this t star, theoretically. Remember, tau, the space-time, is the volume over the volumetric flow rate. The volume of the reactor is known, and the volumetric flow rate is known, so tau is known. Let's say I come up with this number, and then I do the experiment. I actually do that experiment. And I don't get, sometimes I might get the same answer as the theory. Sometimes I may get an answer that's bigger or smaller. Let's look at both cases. What do you think, what happens if I find that I reach 90% of the change faster than I thought? What happens if I reach there faster than I thought? What do you think that's telling me? What can we diagnose in the reactor if we get there faster than we thought? Eric? What's that?
Your CA was higher than you thought.
Possibly. CA could be higher than I thought it was. But let's say I measured CA. I know CA. And I went back and I checked it, and I know CA. What else could be changing? So it says that the characteristic time was shorter than I thought it was. Well, remember with exponential, the characteristic time is tau. So here's tau. Tau was shorter than I thought it was. Well, I'm constantly measuring the flow rate. So I know the flow rate. So if tau is smaller than I think it is, what's it telling me? What am I getting wrong? The volume. How could I get the volume wrong? Well, any ideas how I can get the volume wrong? I could have a buildup of crud in the reactor. I could have so much crud in the reactor that the effective volume is smaller. So if I get a shorter time, that might be a hint telling me I have garbage in the reactor and only part of the volume is accessible. What if, on the other hand, the tau is longer? It takes longer than I thought it should. That one's a little more subtle. What do you think that might tell me? Take a wild guess. It doesn't matter if you get it wrong. This is a guess. You're on the job in your company, and this is what happens. What? We have a leak. Okay, possible that we have a leak. So if we have a leak, then it's almost as if I have more volume. That's one possibility. So, okay, now we're going to go to the plant, we're going to check if there are any leaks. Are there any other possibilities? Think back to your transport class, transport 2. It's a hint. Well, what process, here we're assuming that the mixing is instantaneous and that all I have is flow. In your transport 2 class, you have another method of mass transfer. What was that? What other method of mass transfer do you have in transport 2? Diffusion. You have diffusion. Diffusion could be slow. Why would I have diffusion here? Maybe a part of the reactor doesn't get mixed. Maybe there's a dead zone in the reactor. And the only way to communicate with this dead zone is via diffusion. And diffusion can be very slow. So this could be a reservoir of the old concentration. And it only communicates with the rest of the reactor by diffusion. So that could slow things down. So those are possible reasons why I might not get the right answer when I actually do the experiment. Are there any questions? Now, in your textbook, they make a big fuss about a logical way of doing problems. You state the question. You look to see what the question is and what kind of model you need, CSTR model. Then you look to see what parameters do you have, and what's known and what's unknown. So we knew tau, we knew CA, we knew there was no reaction. So the only unknown was CA. So there was only one unknown, CA of T. And then so that means we need one equation to have no degrees of freedom left. The species balance. We have the CSTR equation. Then you solve the equation, we just solved it, and then you validate the solution. You validate it, say, by doing the experiment, by measuring things. Now, part of that happened, so we went through that, and there's an issue here that I should mention, is that in science and engineering, whenever you have an equation, a general equation, say, here's an equation. This makes a prediction for all possible times, and for all possible CA-ins and CA-in for t less than 0. It makes an infinite number of predictions. I can only do a finite number of experiments. So I can never be 100% sure that my theory is right. So this is a little bit of the philosophy of science. There was a philosopher, I guess it was in the 1950s, Karl Popper, who said, in science we have two kinds of theories. The ones that have been proven wrong already, and the ones that are still hanging. That is, you can never prove a theory right, because theories always make an infinite number of predictions. You can only do a finite number of experiments. So there's always the possibility, even if you've done 100 experiments, that experiment 101 might contradict it. So there are the theories that have been proven wrong already, and the ones that we don't know yet. But the way things work in practice is the more experiments we do that agree with the theory, the more we believe the theory is right. And just to give you an example about how it's hard to draw complete conclusions, Isaac Newton in the, I think it was 1700s, came up with Newton's laws, Newton's second law, among other things. And until 1900 or so, every experiment that people were able to do agreed with Newton's law. And everyone thought, boy, this Newton guy was a genius, and that theory must be right. By the way, Newton also invented calculus, and he invented calculus during a time that's very reminiscent of what we just had. There was a plague in England, and I think it was a bubonic plague. And they didn't have Moderna or Pfizer to come up with vaccines. So all they had was isolation. So he was isolating the country he was from a wealthy family in his house in the country, and he had nothing to do there, so he invented calculus. So there was something good that came out of the plague. But that's something we can identify with. He also didn't have Zoom, so he wasn't bothered with Zoom calls. Okay, so now getting back, he came up with this theory that seemed to agree with every experiment for 200 years. And then they started getting experimental techniques that were good enough to be able to measure the amount of time it took for light to reach from the sun to the earth. And if the sun is here and the earth is spinning, when the part of the earth that's spinning towards the sun, it should take shorter amount of time to get there than the part of the earth that's turning away from the sun. So you would expect a small difference in the amount of time it takes a ray of light from the sun to reach the part of the earth, the side of the earth rotating towards the sun and the side of the earth rotating away from the sun. And by around 1900, the experimental measurement techniques got good enough that they were sensitive enough to detect that difference. And there was absolutely no difference. And that said that there was a problem with Newton's law. That amount of time should have been different, and it wasn't. And that was the basis for the Lorentz equations, which then led to the theory of relativity. So finally, after almost 200 years, Newton's law was proven wrong. It doesn't mean we throw it in the garbage. It means it has a certain regime of validity. It doesn't work when velocities get close to the speed of light, and it doesn't work when you get down to atomic scales. That's where quantum mechanics takes over. But in everyday life, it's still pretty damn good. Okay, so I'm fussing a lot, but I did want to bring up that point about what it means to validate an experiment or validate a theory. Are there any questions? Okay, let's do another problem where already is no longer zero. So we're now at 7 drop. In this case, I have a CSPR. I have a CA in t less than 0, a CA in t greater than 0. So the same thing, CA in, this is t equals 0. There's a step change in the input. But now, I also have a reaction. A goes to B with a rate constant K. And K is going to be given. So this, I think, just to put some numbers in it, let's use the numbers they use in the book. It's 0.925. So this goes from 0.925 to twice 0.925. So 1.85. And K is equal to 0.04 per unit time. It's the first order reactors. So let's solve this problem. And we need a question. So the question is, we have a CSPR, and we're given, there's a maximum CA max before you start causing trouble is 0.85. So when we reach 0.83, we want an alarm to go off so that we don't let it go to 0.85. We want an alarm to go off. Okay, now you might say, silly problem. When CA starts out at 0.925, that's higher than 0.85. It's not what's in the reactor, it's what comes after the reactor that doesn't want a high CA. So the reactor can handle 0.925, but the next piece of equipment can't. So we don't start connecting the next piece of equipment well. So what comes out of the reactor is not what comes into the reactor because we have a reaction. So again, let's take a picture here. I've got CA in coming in, and I have CA coming out. But here I have A goes to B. So what comes in, a lot of it gets chewed up by the reaction. So what comes out is less than what comes in. Yeah. So now let's rewrite the CSTR equation. Now, if the rate of reaction is minus KCA, so if RA is minus KCA, I got to move that to the other side of the equation because it's a CA. So I have RA is minus KCA. Remember, RA is the moles. Yeah. It's the net rate of production of A. A is being consumed, so it comes in with the negative sign. It's being destroyed. And it's in moles per unit time. Moles, so K is per unit time. So it's the same for me. Okay, so now I have PCA dt. And similarly, I had CA over tau. But now I have a minus KCA here, so I have to add that to the other side of the equation, plus KCA. And that's equal to CA in over tau. So let's rearrange this thing here. K plus 1 over tau is equal to 1 plus K tau over tau. So I'm going to put that under, I multiply and divide by tau and add them. And I can write this as 1 over T, where T is a time constant. Now let's notice, how do I know that? Tau is units of time, K is units of inverse time. So K tau is dimensionless, plus 1 is dimensionless, the numerator is dimensionless, the denominator is time. So this has units of 1 over time, and I'm going to call that a new time constant T. And notice that T, let's write it out over here, T is tau over 1 plus K tau. T is tau divided by a number greater than 1. So T is smaller than tau. When K is greater than 0. Meaning, the time constant is faster. The time constant governing the system, the characteristic time of the system, is faster when I have a reaction. Of course it's faster, because it used to be the flow is what took A out of the reactor, what reduced A. Now I have something else also reducing A, the reaction and the flow. So I'm reducing A faster, so the time constant is faster. And the new time constant is T. So when I rewrite this, I get dCA dt plus CA over T is equal to CA in over tau. Here I have T now instead of tau. And now I can again, luckily, this is a constant, and this is a constant. So A, what's A? Someone want to help me here? What's A? 1 over T. And what's B? CA over tau. Both of them are constants. Again, T1 is 0 here, because this happened at 0. And Y is CA. So I can write out the solution. CA of T minus CA of 0. CA of T minus CA of 0. Where did I write that? So here's the constant. Here's the, actually, let's write it from here. CA of T. So let's appeal to this equation. That's equal to CA of 0 times e to the minus A, T1 is 0, so e to the minus little t over big T. Plus, go to the next line, plus V over A is CA in divided by tau divided by T. So times T over tau. And let's notice what T over tau is. T over tau is 1 over 1 plus T tau. Times, that's B over A, times 1 minus e to the minus. So notice, unlike the previous case, somebody can't read? The exponential is e to the minus little t over big T. In both cases, it's the same one. Notice that the time constant that the exponential decays, the exponential time constant, is no longer tau as it was here with no reaction, it's t. It's t. And notice that I have not just CA in, which I had over here, but now I have CA in over 1 plus K tau. And let's look at the steady state. So in steady state, which is t less than 0, at steady state, t goes to infinity. So that says that CA of 0, which is the steady state, because for t less than 0 is the steady state. So here is the steady. That's, yeah, so CA of 0 is, well, t less than 0. So this was equal to, at t goes to infinity, this drops out, and it's equal to CA in for t less than 0, divided by 1 plus t. Or CA for t less than 0 over CA in for t less than 0 is equal to 1 over 1 plus t. So the steady state concentration of a CSUR, when I have a CA8 for t less than 0, is not CA8. Here it was CA8 because there was no reaction. Here it's less than CA8 by a fraction of 1 over 1 plus K tau. If the reaction was 0, if there were no reaction, then it would just be 1. That would be that expression. But it's less than that. Similarly, I know that as t goes to infinity, I also get steady state. And then I will also have that CA as t goes to infinity over CA in for t greater than 0 is also going to be 1 over 1 plus K tau. The same calculation. Just here it was for t less than 0, here it's for t greater than 0. So I know these steady state concentrations. For t less than 0, it was at steady state, because that was the given. For t greater than 0, it's not an instantly steady state, but eventually it gets there as t goes to infinity. So eventually again. Any questions? So, get it in an even form, is that right? That's fine. Okay, so here we have the solution. And let's notice that I can write CA0, which was CA of t less than 0. Let's rewrite it. This is CA of t. CA of 0 was CA of t less than 0. It was CA in at t less than 0 over 1 plus K tau. So I plug in this guy is this guy, so I plug this over this. E to the minus t over tau. Plus CA in for t greater than 0 over 1 plus K tau. 1 minus E minus T over T. So all I did is I took the solution and I identified T over tau, CA of 0, and CA in. So here is my solution. And now the question is, how do I answer the question? How long will it take to get to point A3? So I can say CA of T is 0.83 or 0.85. And that's equal to CA in T less than 0. That's 0.925. Over 1 plus K tau. 1 plus K is 0.04. And I think we're given tau, which I didn't tell you. So let me do that. Okay, so I took this equation. Are you happy with this equation? Okay, so T over tau is 1 over 1 plus K tau. That's this. This is happening for T greater than 0. So this is CA in for T greater than 0. So that's this. The initial condition was the steady state corresponding to this. So I looked, what was that steady state? That steady state was the steady state for T less than 0. So it was CA in for T less than 0 over 1 plus K tau. CA in for T less than 0 over 1 plus K tau. Okay? Other questions? Okay, so I have to tell you what tau is. I didn't tell you what tau was. Where's tau? Somewhere I have the value for tau. Tau was given as 24.7. So I'm just plugging in e to the minus t over tau, t over big T. Well, big T is tau, which is 24.7, divided by 1 plus 0.04 times 24.7. So that's whatever that is, t. And then I have plus CA in at t greater than 0, which is 2 times 0.925. Over 1 plus 0.04, 24.7. Times e to the minus t over big T. So all I have to do here is, this is 1 minus. So the only unknown here is t. So I think you can see here, since the rest are just numbers, that I can solve for t star. So I get a certain value of t star when the concentration is 0.83. Is that clear how to solve this? Yes or no? Are you waiting? Okay, so we get the value. And so what am I going to do? Let's say I get to times 5 is 312. Okay, so I have this system, and I make the step change. And by the way, the first thing you can calculate is 1 over 1 plus k tau with these numbers. This is 24.7 times 0.503. Plug in. So 1 over 1 plus k tau is about a half. So it's about a half. So what comes out here, this is about a half of CA. So that says before t is equal to 0, even though 0.925 is coming in, you've got about 0.646 coming out, which is a lot less than 0.83. So it's not like I'm in danger initially. When I double that, then I can, eventually, if I wait for steady state, I'm going to have roughly half of twice 0.925. It's about 0.925, that's higher than 0.85. So clearly, the solution, which is, we can rewrite the solution. Let's just collect the exponentials. So I've got CA in t greater than 0. actually, let's factor out 1 over 1 plus k tau times. So here I have CA in for t greater than 0. This term, the 1. And then I also have plus CA in for, actually, what am I minus? CA in for t greater than 0, this term, the minus, and this term with a plus, minus CA in for t less than 0, times e to the minus t of big T. So I just rewrote that same equation where I put the two exponentials together. So notice, what does the solution look like? I've got a constant minus another constant times an exponential. So again, an exponential looks like this, minus an exponential looks like that. So I've got a constant minus an exponential. So again, I'm going to get something that grows. I'm going to get something that grows. But it's not going to grow from here to here. It's going to grow. So what's the solution going to look like? CA versus I'm going to have some value, which was CA in for t less than 0, over 1 plus k tau. So it's less than 1.25. It's about half of that. And I know that on large times, I'm going to get to twice that. So I'm going to get 2 times 0.925 times 0.513. And I'm going to go from here to here as with a negative exponential, like a negative exponential, subtracting a negative exponential. But the time constant here is t, right? So it's faster than the time constant here, which was tau. Here it was tau. And I don't want it to go all the way here. This is too big. I want to cut off at about 0.83. So I look at that time point, t star, where I get to 0.83. And then I want to take corrective action, because I don't want it to keep going along this curve. What do you think the corrective action I should take might be? How will I keep the concentration from continuing to go up? What corrective action should I take? What would you do? You're on the job, you're in the plant. You know that once it reaches 0.85, then the stuff downstream, the catalyst downstream is going to get destroyed in the next reactor. So what do? The alarm just went off, it's 0.83. What do? How do I make sure it doesn't keep going up? Your boss is waiting, and she has a short temper. We should what? Down the reactor? Where? In which stream? Yes, good idea. Maybe we should go back to the original value. Maybe at T star, we should go back to here. Because as soon as we start putting less in the reactor, that's going to start lowering the concentration. So notice this happens at T star. If I want to calculate what happens there, once I've done that, that didn't happen at 0, it happened at T star. So what's going to happen? I'm going to get a decrease to here, an exponential decrease. The solution is going to look the same, except instead of t's, I'm going to have t minus t stars. I'm going to have t minus t star. So it's going to look very similar, but I'm going to have t minus t stars because the change happened at t star, it didn't happen at 0. I'll let you figure that out, write that out as an exercise, what that solution would look like. So that's going to be a homework problem to test to go through that. Well, we only have about 10 minutes to go. So let's start the next problem. Someone want to take a picture of that blackboard because There's too much glare here, so I'm going to write just this blackboard is the only one I need. I'm not, okay? I'm going to leave that up because of that. Okay, so now let's look at the following case. Let's say I have two CSVRs in series. So I've got CSVR V1 and V2, and I've got a V and CA. And here I have a CA1, and here I have a CA2. So out there in series. And let's remind ourselves about the CSVR equation, which I just conveniently erased. So I have VCA, and I'll call it CAI for reactor 1 and reactor 2. I equals 1 and 2 is equal to CAI in minus CAI over tau plus RA. And here I also want a reaction. I'm going to have the same reaction A goes to B. Okay, so RA is minus K CA. So let's rewrite this. This is VCAI dt plus CAI over tau I. And this is minus KCA. So then I have plus K, which is equal to CAI in over tau I. Where this thing now is 1 over TI. Where TI is equal to tau I over 1 plus K tau I. Just like before. And right here, this is for reactor 1 and reactor 2. I equals 1 and 2. So let's examine the difference between reactor 1 and reactor 2. And again, let's assume that CA in, here's T, here's 0, makes a step change from T less than 0 to T greater than 0. So CA in has a step change. And we know that CA1, that's the problem we've solved already. We don't have to solve it again. We did that already. CA1 was at steady state. This steady state was CA in over 1 plus K tau 1. Maybe I should just write it bigger since I was writing too small. CA1 over CA in over 1 plus K tau 1. And we know that eventually it will reach CA in, this is T less than 0, T greater than 0, over 1 plus K tau. But we know, because we just solved it, that it's going to go like this, that there's 1 minus an exponential with the time constant T1. So that's all we solved already. But the difference is, for reactor 2, what's the inlet to reactor 2? The outlet from reactor 1. So the outlet from reactor 1 changes with time. It's not a step function. So this guy for CA2, CA2 in is equal to CA1 out, which is a function of time. It's not a step function anymore. Dorothy, we're not in Kansas anymore. It's not a step function anymore. So when we use this equation, now B is no longer a constant. So we have to use this equation. Well, let's go ahead and do it. We have time to do anything? Sure, we have 5 minutes. That's an infinite length of time. And this is blackboard number 4. Okay, so let's start doing it. All So we know that the solution, so we know A and B. Okay, so let's write out the solution. I've got CA1, I know. It's the same solution I had over there. This is CA1. This is all CA1. I don't have to rewrite it. How about CA2? CA2 of T. That's equal to CA2 of 0. CA2 of 0 was the steady state. We have to calculate what that steady state is. Times e to the minus the integral. A is still a constant. A is a constant, so I'm okay there. This is e to the minus A, so it's 1 over T, T2 times T, because T1 is 0. Plus e to the minus T over T2. A is a constant. A is just 1 over T2, so that's easy. Times the integral of e to the plus T over T2 from T1 to T of B of T prime. B is CA1. CA1, where is it? CA1 is this guy. One over 1 plus A tau 1. So I'm running back and forth, copying it. Times CA in of T greater than 0. Minus CA8 of T greater than 0 minus CA8 of T less than 0 times, did I get that right? Greater than 0, less than 0? Yeah. Times e to the minus T prime over T1. And instead this should have been CA in 1, not CA in 2. dt prime. Because this whole thing, with the 1 over 1 plus KT1, is CA1 of T, which is what I needed here. And I have to divide, of course, by tau 2. So now I just have to identify things and do the integral. So let's say I'm not going to be able to do the integral today because I'm going to run out of time. But what is CA2? CA2 of 0. CA2 of 0 was the steady state of 2 CSTRs in series. It was the steady state. So remember, what we found was the steady state. The steady state was the input divided by 1 over 1 plus k tau. So let's notice that CA2 of 0 was the steady state before t equals 0. This of CA1 before t equals 0. So that was so what is that? That's equal to the steady state of CA1 was CA in t less than 0 divided by 1 plus k tau 1. That was the steady state. The output here, the steady state here, 1 over 1 plus k tau. So we've identified this guy. What else do we need to identify? Well, we need to identify, we don't really have to identify anything else, we have to do the integral. We can't do the integral today because we're going to be out of time in a minute. But we have to be careful. Notice, here I have an e to the t prime over t2, and here I have an e to the minus t prime over t1. There are going to be two situations. In one case, t1 and t2 are different. Why would t1 and t2 be different? Because of e1 and e2. In which case, I'll still have an exponential in here. But, and when I integrate an exponential, I'll get the exponential back divided by a constant. So I'll have an exponential. The interesting case is if T1 and T2 are the same. If T1 and T2 are the same, this and this will cancel. And I'll just be integrating a constant and another constant, dt prime. When I integrate a constant dt prime, I'm going to get a factor of t. And that's going to be t times an exponential. So when they're the same, I'm going to get t times an exponential, and I'll do the details next time. When they're different, I'm just going to get an exponential. And that's the issue of resonance. If you remember from your freshman physics class, you can get resonance, you get powers of t times exponential. And we'll see that next time. That's coming attractions. Yes.
I'm sorry, what's CA2 again?
CA2, the concentration at the outlet of reactor 2.
Then if it's out the outlet of reactor 2, what would you find it using the time equal to 0 to reactor 1?
Because the inlet to reactor 2 is the outlet from reactor 1. So what comes into reactor 2 depends on what happened in reactor 1.
Okay, because it's dependent on resolution. All right.
Other questions? Okay, I think we're about 2 minutes over.